There's a world where a human being has never stood, where the atmosphere is too thin to breathe, liquid water can't normally remain stable on the surface, and a single mistake could become fatal in minutes. And yet, this may be the first planet beyond Earth where humanity eventually builds a permanent presence. Mars. It's about half the diameter of Earth, separated from us by hundreds of millions of kilometers, depending on where the two planets are in their orbits. We've already sent machines there. They've driven across its surface, drilled rocks, photographed ancient landscapes, and searched for evidence that liquid water once existed there. But humans are different. A robot can survive years without food, oxygen, or a return ticket. A human can't. So why are space agencies and engineers spending years developing the technology needed to send people across interplanetary space? Because Mars isn't simply another destination. It could become the ultimate test of whether our species can operate on another planet. And here's the question that changes everything. If we eventually send humans there, what will the first explorers actually find? A dead world? The remains of an ancient habitable environment? Or a planet that could teach us how worlds change, and perhaps how Earth itself might one day change? The journey has already begun, and the first destination may not be Mars itself. For decades, Mars existed mainly in our imagination. It appeared in science fiction as a world of canals, alien civilizations, and mysterious cities. Then spacecraft started getting close enough to replace imagination with evidence. The picture changed dramatically. Mars turned out to be a cold, dry desert with a very thin atmosphere, dominated by carbon dioxide. Its surface is covered by impact craters, enormous volcanoes, vast valleys, and landscapes shaped by processes that occurred over billions of years. And yet, Mars wasn't always the world we see today. Evidence from orbiters and rovers shows that ancient Mars once had environments where liquid water flowed across the surface. There were rivers. There were lakes. There were ancient sediments. NASA's Perseverance rover is exploring Jezero Crater, a location selected partly because geological evidence indicates it once contained a lake and river delta. That matters because liquid water is one of the fundamental ingredients scientists consider when evaluating whether an environment could have supported life. But habitable doesn't mean inhabited. That's a crucial distinction. Scientists haven't discovered confirmed evidence of ancient Martian life. What they have found is evidence that some ancient Martian environments had conditions that could have been suitable for life. And that raises a haunting possibility. What if Mars didn't always look dead? What happened to its atmosphere? Where did its surface water go? And could traces of that ancient environment still be locked inside rocks beneath the surface? Those aren't science fiction questions anymore. They're scientific research questions. And humanity now has machines on Mars capable of investigating them. But the moment we put humans there, the scientific challenge becomes something much bigger. We have to keep the humans alive. Here's the first crack in the simple idea of just go to Mars. Getting there is difficult. Staying there is much harder. Mars has an atmosphere, but it is extremely thin compared with Earth's. That means astronauts can't simply step outside wearing ordinary clothing. They'll need spacesuits providing pressure, oxygen, and thermal protection. They'll also face radiation from space and from solar activity because Mars lacks Earth's global magnetic field and has a much thinner atmosphere to provide shielding. Then there's the journey itself. A Mars mission isn't like flying from one continent to another. Earth and Mars orbit the Sun at different speeds and distances. Efficient missions generally launch during windows when the planets are suitably aligned, which occurs roughly every 26 months. Once you're on your way, you're committed to a journey lasting months. And communication isn't instantaneous. Depending on the positions of Earth and Mars, radio signals can take several minutes to travel one way. That means astronauts won't be able to depend on Earth for immediate instructions during every emergency. Imagine something breaking: a pressure leak, a computer failure, a medical emergency, a malfunction in a life support system. The crew may have to respond before anyone on Earth even knows what happened. This is why NASA's current Moon-to-Mars architecture doesn't treat Mars as a single rocket launch. It's a whole system: transportation, habitation, power, communications, robotics, surface mobility, resource utilization, and, critically, a way to get the crew home. NASA's current architecture specifically identifies the need to develop the capabilities required to travel to Mars, land safely, live and work there, and return safely to Earth. So the real question isn't simply, can humans reach Mars? It's, can humans survive Mars long enough to accomplish something meaningful? And that distinction changes the entire mission. Scientists and engineers aren't starting from zero. We've spent decades learning how humans behave when they're isolated from Earth. The International Space Station has provided an enormous amount of experience with long-duration spaceflight. Astronauts have learned how to exercise in microgravity, recycle water, maintain complex systems, and live with limited supplies. But Mars introduces a completely different environment. On the Moon, astronauts are only days away from Earth. Mars is vastly farther away. The Moon also has almost no atmosphere, while Mars has a thin atmosphere that creates its own engineering challenges. And unlike the International Space Station, a Mars crew can't simply return home if something goes seriously wrong. So what would astronauts actually do? Science would be a major part of it. They could study Martian geology directly. They could examine rocks that have remained undisturbed for enormous periods of time. They could investigate the history of water. They could search for chemical evidence associated with ancient environments. And humans have one enormous advantage over robots: adaptability. An astronaut can look at something unexpected and change the plan. A robot follows its programming, although increasingly sophisticated autonomy can help. That human-machine partnership is likely to be crucial. NASA's Moon to Mars architecture explicitly includes autonomous systems and robotics, infrastructure, mobility, habitation, and in-situ resource utilization as parts of the overall exploration system. But there's a deeper question. If we're serious about sending humans to Mars, should we simply take everything they need from Earth? Or should Mars itself become part of the solution? That question leads directly to one of the most important technologies in future planetary exploration. Imagine landing on Mars with every kilogram of food, water, fuel, and construction material already packed inside your spacecraft. It sounds safe, but there's a problem. Mass is expensive to transport between planets. The more supplies you need, the more challenging the mission becomes. That's where in-situ resource utilization comes in. The phrase sounds complicated, but the idea is surprisingly simple. Use resources where you find them. NASA's Moon to Mars architecture includes in-situ resource utilization systems designed to extract resources from the Moon or Mars and turn them into useful products. On Mars, one of the most important possibilities involves water. Scientists know that water ice exists in the Martian subsurface and at the poles. If future explorers can access suitable deposits, that water could potentially be used for drinking after processing. It could also provide hydrogen and oxygen. And oxygen has another enormous use: rocket propellant. The concept is important because bringing all the propellant required for a return journey from Earth would add enormous mass to the mission. NASA's Mars architecture studies therefore consider different approaches to ascent systems and explicitly examine whether propellant could be produced on Mars using local resources. But producing resources on another planet isn't as simple as digging a hole. Equipment has to arrive first. It has to work reliably. It has to survive dust, cold, and radiation. It has to operate with limited human assistance. And if the system fails, the crew can't simply order replacement parts from Earth and expect them tomorrow. That's why robotic preparation could become essential. Robots could potentially survey landing zones, move equipment, prepare infrastructure, and help establish power systems before humans arrive. The Moon is also becoming a test bed. NASA's current strategy is designed to use lunar missions to demonstrate technologies and operational approaches that could eventually support Mars exploration. But here's where it gets really interesting. Mars may not be the only world humanity is preparing to understand, and one distant moon could completely change the way we think about the search for life. That world is Europa. Europa doesn't look anything like Mars. It's an icy moon orbiting Jupiter. Its surface is brutally cold. covered in water ice and marked by fractures and strange reddish material. But beneath that frozen shell lies the reason planetary scientists are so interested. There is strong evidence that Europa contains a global saltwater ocean beneath its icy crust. NASA estimates that this ocean could contain more than twice the amount of water found in all of Earth's oceans combined. And this changes the meaning of habitable. A world doesn't necessarily need a warm surface and blue sky to potentially support life. On Earth, ecosystems exist in places where sunlight barely matters. Deep beneath the ocean, chemical energy can support life. That's why Europa is such a compelling target. NASA's Europa Clipper spacecraft launched on October 14, 2024, and is traveling toward Jupiter. It is scheduled to reach Jupiter in April 2030, and then conduct 49 close flybys of Europa during its mission. Its goal is not to directly detect life, but to investigate whether Europa has conditions suitable for life. And this is the twist. The world humanity may eventually visit isn't necessarily the world most likely to contain life. Mars is comparatively accessible for human exploration. Europa may be scientifically fascinating because of its hidden ocean, but Jupiter's radiation environment makes human exploration there extraordinarily challenging. So our future may involve a division of labor. Humans could explore Mars directly. Robotic spacecraft could explore much more dangerous worlds like Europa, and each mission could answer questions that influence the next. If Europa's ocean turns out to have the right chemistry for life, would that change where humanity focuses its exploration? And if Mars contains evidence that life once existed there, would that make the search for life on Europa even more urgent? Drop your biggest space question in the comments. Because we're approaching the point where our exploration isn't just about visiting places. It's about finding out whether life exists anywhere else. But let's come back to Mars, because there's something remarkable about its position in our exploration strategy. NASA's current Moon-to-Mars architecture describes a gradual pathway: return humans to the Moon, develop and demonstrate technologies there, establish increasingly capable infrastructure, and use those lessons to prepare for Mars. The Moon becomes a proving ground. Not because the Moon is Mars. It isn't. But because the Moon allows engineers and astronauts to test systems much closer to Earth. Power systems, habitats, surface mobility, communications, robotics, resource extraction, operations. The goal is to learn before the stakes become interplanetary, and that gradual approach matters, because Mars has no room for improvisation. Consider power. Solar panels can work on Mars, but dust is a serious operational concern, and sunlight is weaker than it is at Earth. A future crew could potentially need multiple power sources and robust energy storage. Then there's shelter. A habitat must maintain pressure and temperature while protecting astronauts from radiation and the Martian environment. One potential strategy is to place habitats beneath or behind layers of Martian material. The principle is straightforward. Mass above you can provide shielding. Then there's food. A short mission could rely heavily on supplies brought from Earth. A longer presence would require increasingly sophisticated systems for recycling water, managing waste, and potentially producing some food locally. None of these challenges is solved simply because we can land a spacecraft on Mars. That's why a human Mars mission isn't one technological breakthrough. It's hundreds of systems working together. And the most dangerous component is still the one sitting inside the habitat: the human body. Mars forces us to confront something we've never truly had to confront before. How do you keep humans healthy when Earth is no longer nearby? Reduced gravity is one concern. Mars has only about 38% of Earth's surface gravity. We don't yet know all the consequences of spending many months or years in Martian gravity. Radiation is another. A Mars crew would experience radiation during the journey and on the surface. Then there's isolation. Imagine seeing Earth as nothing more than a bright point in the sky. Your family is there. Your entire civilization is there. But you're millions of kilometers away. And sometimes communication takes minutes each way. Psychology becomes part of spacecraft engineering. The habitat must be a home, laboratory, machine shop, shelter, and lifeboat all at once. And that's why Mars could become much more than another destination. It could become a test of whether humans can become a genuinely spacefaring species. Not because one astronaut plants a flag, because a sustainable presence requires systems that can operate repeatedly. NASA's long-term architecture explicitly discusses progressively longer and more complex Mars missions after an initial human journey, rather than treating a single landing as the end goal. That changes the vision. The first crew wouldn't necessarily be going to Mars to build a city. They'd be proving that humans can survive, work, and return from another planet. Later missions could build upon that experience. More infrastructure, more science, more autonomous equipment, more local resource use, maybe eventually, a continuously occupied outpost. But that word, eventually, matters. No current plan guarantees a permanent city on Mars. And nobody should confuse an architectural roadmap with a scheduled settlement. We're still solving the basic problems. And there is one final question that may be even bigger than whether we can get there. Should we? If you were offered a one-way seat on the first human mission to Mars, with the promise that you could return, but only after years away from Earth, would you go? If this changed the way you see humanity's future, hit like and subscribe for more research-based stories about the worlds we're learning to reach.